I'm going to walk you through this question from 2000, and then I'm going to have you try one on your own. This is the question that we saw in class, but we didn't actually get to do. Oops, sorry about that. Part A is pretty similar to other Part A's that you see on problems like this. We're given the derivative, we just have to show how to get from the original equation to the derivative. And if we take a look at this, and just like when we went over the homework, I first scope it out for product rules, and there are two of them here, so just be careful. When I take the derivative of xy squared, I'm going to have f g prime plus f prime g. So that whole thing is the derivative of xy squared. Now we need the derivative of the minus x cubed y. So I'm going to have f g prime plus f prime g. So those two terms are the derivative of the minus x cubed y. So notice that I kept the negative with the x cubed. That is to help me so I don't make any sign errors here. So that whole thing is my left side, the equals 6, its derivative is just 0. And then from here, we are in more of our comfort zone. We are going to get the dy dx by itself. If I do a couple steps at once, hopefully we can follow. I am going to group the two dy dx terms on the left, and I'm going to factor out a dy dx. The remaining terms I'm going to put on the left. I have a minus y squared and a plus 3x squared y. Now I look at this and I look at theirs and I notice that I wrote the numerator a little bit backwards, and it doesn't hurt just to make sure that we get full credit on the problem. For part B, we are getting a little trickier, so we're looking for points on the curve. The x-coordinate is 1, and then we want tangent lines for each of these points. So a little bit of a red flag that we're going to get more than one point here, so let's just be aware of that as we go. So anytime we're looking for a point, we are looking at the original equation. So we have slope from the derivative, points come from the original curve. So I'm going to go back and look at that original equation. I'm looking for points on the curve with an x-coordinate of 1. So I plug in 1 for x. And if I plug in 1 for x, this actually simplifies really nicely. So I'm trying to solve this because I want to know what the points are. And this factors pretty well. I'm getting 2 values for y, which makes sense because the problem hinted that we were going to have more than one point here. So I have 2 y values that go with my x value of 1, so I have 2 points. I have 1, 3, and then I have 1, -2 as my 2 points. Unfortunately, this is not the end of the problem because we want the equation for the tangent line at each of these points. So I'm not done. I need 2 tangent lines because I have 2 points. Well, I have the points. We know that for a tangent line, we always need a point and a slope. I have both points, but I need their slopes. So starting at 1, 3, I use the derivative to get the slope at 1, 3. 3 times 1 squared times 3 minus 3 squared. So I am, oh, that simplifies. 2 times 1 times 3, 6 minus x cubed is 1. So this is going to give me 0 for a slope, because that's going to be 0 over 5, which is just 0. So y minus y1 equals m times x minus x1, and I have my equation. I could rewrite this to y minus 3 if I wanted it to look a little bit nicer. Okay, looking at the other points, so at 1, negative 2, we need to do the same thing. So what it is that I'm doing here, if you missed what was going on, I'm taking this expression for dy dx, and I'm plugging in my point x comma y in for x and y in the derivative. So I have my dy dx, and if I plug in 1, negative 2 in for x and y, I'm going to get negative 6 minus 4 over negative 4 minus 1. What's that? Negative 10 over negative 5, so that's 2. Y minus y1 is m times x minus x1. So I have my two lines, and I am all set. So this question, just to give you an idea, this was worth 4 points. This line here, that was worth 1 point. Getting the two separate y values, that was worth a point. And then the tangent lines were worth 1 each. All right, that brings us to part C. We want to know where the tangent line is vertical. These types of questions almost always have a part where you have to find a vertical or a horizontal tangent line. And what you have to remember, tangent line means slope. Derivative means slope. A tangent line has an undefined slope. That is going to represent, in our derivative, a vertical tangent line. What we do is we look for where the denominator is equal to 0. That's because a vertical tangent line, remember, has an undefined slope. Undefined slope, or undefined fraction, is where our denominator is 0. If we want to know where a tangent line is horizontal, that's where we set the numerator equal to 0. Now, these questions almost always involve some sort of system of equation, but let's see what happens when we start this out. So, oh, and I should specify, this is of the derivative. So here we're working with the slope. Undefined slope is a vertical slope. So since we're talking about slope, we're talking about dy dx. So if I look at dy dx and I want to know where the tangent line is vertical, I want to know where the slope is undefined, that means I want to know where that denominator is equal to 0. So I need to solve this equation. And unfortunately, I don't get that far with part of it. So I have x equals 0, and I have 2y equals x squared. So we have two possibilities that we can work with. Either x is 0 or 2y is x squared. It's very tempting to just circle x equals 0 and then move on from the problem, but unfortunately, that's not going to get you the right answer on this one. So what we need to do, in these questions, like I said, they usually involve some sort of system. We have x equals 0, we have 2y is x squared. We've worked with the derivative, we've sort of run out of things we can do with dy dx. That means we have to go back to the original curve. And let me switch my color. We have two things that we can work with. I have when x is 0, and if I plug that into the original curve, I get something that doesn't make sense. What that means is there are no points on the curve when x equals 0. So unfortunately, the nice answer, x equals 0, is not the right answer. I'm going to have to work with this a little bit more. So if I have 2y equals x squared, and I am going to write this as y equals 1/2 x squared. And if I do the same thing here, and I'm plugging in 1/2 x squared for y. So I have 1/2 x squared squared minus x cubed times 1/2 x squared. A little bit awkward, but that doesn't mean we can't do it. X times 1/4 x to the 4th minus 1/2 x to the 5th equals 6. 1/4 x to the 5th minus 1/2 x to the 5th equals 6. If I multiply everything by 4, I can clear this fraction pretty quickly. I would have a negative x to the 5th equals 24. X to the 5th is negative 24. And x is the 5th root of negative 24, which turns out to be the right answer to this question. So these questions, you do have to be a little careful that when you get an answer, and here the nice answer was x equals 0, but on all of these problems, when you get your answer, especially if you're working from the derivative, you always need to double check by plugging them back into the original function. And oftentimes, when you plug back into the original, you're going to have a D&E situation somewhere. So just be very aware of that and make sure that you read the problem carefully.